Okay, we're going to do a quick corollary of the short tower law, and this is also called the tower law. But again, um, as I said, there whenever you use either the short tower law or just what I'm about to write down, it's just called the tower law. I've never heard anyone refer to something as the short tower law. I'm not saying it's not done, but I've just never heard it. So suppose you have an honest tower of extensions. So you have some an extension followed by an extension followed by an extension, and there's n plus 1 fields here. So some number of fields that's at least 2. Okay? Well, I mean, this statement makes sense for any n bigger than or equal to 0, but in practice, some number of extensions that's at least 2. So these are subfields of C. Then the degree of the large extension is the product of the degrees of each successive extension. And the proof is direct application of the short tower law. So we proceed by induction. And as a pro tip for induction, if you can start something at n equals 0, start it at n equals 0. So if n equals 0, what does this say? It says that k0 over k0, we could, of course, add a k0 term, that's of course 1, is equal to the degree of k0 over k0, and both of these are 1. Well, they're just the same thing. I guess them being 1 is not relevant for the proof. But that's what this equation would say. Great. If you don't like n equals 0, you can do the same thing with n equals 1. This, for n equals 1, would say the degree of k1 over k0 is the degree of k1 over k0. Okay. All right, so that's the base step. For the inductive step, we are going to assume it holds for successive extensions of length n and prove it for length n plus 1. Okay, so to that end, we need to take an extension of length n plus 1. So suppose k0 contained in k1, contained in kn, contained in kn plus 1 is a tower of subfields of C. By the short tower law, and I'm only calling it here, that way I can reference, it would be bad to be self-referential, right? I'm referencing the previous version that we proved. The degree of kn plus 1 over k0 is what? Well, I want to view k0 as a subset of kn as a subset of kn plus 1. So those are my 3 fields involved in the short tower law. So we're going to look at the degree of kn plus 1 over kn times the degree of kn over k0. Okay. All right, so that's true by the short tower law, but the tower of extensions here is of length n. So by the inductive hypothesis, we can say that this degree is equal to the degree of kn plus 1 over kn still, but then this second one here, we can rewrite as the degree of kn over kn minus 1 times the degree of kn minus 1 over kn minus 2, all the way down to the degree of k1 over k0, because that's a situation where we can apply the inductive hypothesis. All right, so that's the sort of, if you want, the long tower law or just the regular tower law, although they're both the same thing. Let me give you one instance where you might use this. So as an example, we can consider, well, let's do this. Let's enumerate maybe n distinct primes. So pick your favorite n primes, p1, pn. Then we can compute then we have an extension, right, where we take q sitting inside of q adjoin root p1, root p2, root p3, all the way up to root pn. So this is an extension. And we might wonder what its degree, what is its degree? So what is the degree? Okay, well, we can view this as a tower where I first add in the square root of my first prime, and then the square root of my second prime, and then the square root of the next prime, all the way up to the square root of all the, adding in the roots of all the primes involved in this finite list. All right, and what this tells us then, the tower law says that the degree of the large extension is the product of each of these intermediate guys. This is where it's helpful when you're writing this out in LaTeX to copy and paste. All right, and then times all the way down to q adjoin root p1 over q. And since our primes are all distinct, that was important, each time we add in a root, it's going to be honestly new. Now that is me brushing some stuff under the rug, but moral homework, try to prove that. But my point is that each of these extensions is quadratic. Okay, there's n plus 1 fields in our tower here. That means there's n jumps. The jumps are the different extensions. So there's, each of them is degree 2, because we just add in a square root, but there's n of them. So we get something of degree 2 to the n. Okay. All right, so that's an example using the tower law in full generality.